Okay, so sine and cosine, I feel like we really dove into that one pretty hard, right? So now I'm just going to give the basics of this 9.4, this graphs of other trig functions. We're just going to hit the basics, and then you're going to approach it the same way that we did those other ones. So, pardon me, so then you just go right into that. So the first one we're going to look at is secant. So it's the same kind of deal here. We're just going to get our basic, here, let me move this down just a tad, honestly. Our basic secant function. Now, here's the deal whenever it comes to secant. I'm going to make this a 1, this a -1, pi over 2, pi, 3 pi's over 2, and 2 pi. The same kind of thing that we did before with our sine and cosine. Can't do two things at once, apparently. Okay, so, but here's the deal. What do you know about secant? Like, what do we know about our reciprocal identities here of secant? Oh, so it is the reciprocal. So if we come over here, secant x is equal to 1 over cosine x, right? Okay, so keep that in your own noggin there. When I go to graph secant, or cosecant for that matter here shortly, we're just going to be bouncing off of the reciprocal function. So this means my secant graph is just simply going to bounce off of y is equal to cosine x. So we spent so much time on sine and cosine because basically anything that you do for secant, every single transformation, everything, you are going to graph that secant function first and then just bounce off of it. That's it. So when you graph secant, you don't actually graph secant first. You graph cosine, and then whatever you get from cosine, then you just bounce off of that for secant. Okay, check it out. Now for our cosine graph, we know that we start up here, we cross over, we come down, we cross over, and we come back. Now, let me get this big one off of there. What happens here? Cosine's in the denominator. So if cosine is 0, what happens when you have this 0 denominator? Undefined, right? Well, check it out. For my secant graph, let's just go black because we're on this one, so it's okay. For my secant graph, everywhere cosine is 0, I'm going to have an asymptote. So over here, it's the same concept. Whenever I'm having this graph, everywhere I'm at 0, we have asymptotes. And then where I'm at up here at this top, I'm literally just bouncing off of that graph. Because cosine, quote unquote, I'm air quoting that you can't see, starts at 0, whenever I do one of these periods, here is one period, right? Because this is one period of cosine. That's one period here of secant. So if that's one period, then what is the period here of secant? 2 pi, right? It's the same. Good. So my period is 2 pi. What is my range? Well, that's a little tricky, right? Because I'm just up here and then down here. Am I in this middle part at all? No. So because I'm not in that middle part at all, I'm going from negative infinity up to -1 union with 1 to infinity. Because at 1, 1 counts, right? I'm up to that 1 value, but then I'm going down to infinity otherwise. How do we account for our domain? That's also a little crazy because we have those asymptotes in there, right? Okay, so our asymptotes happen where? At every what? Every pi over 2. Do you see that? Pi over 2 asymptote, an additional pi over 2 asymptote. Go back, pi over 2 asymptote, additional pi over 2 asymptote. So at every pi over 2, that's where I get that. So my asymptotes here for secant are going to be at every pi over 2. So I write it like this. X such that X cannot equal. So let me say this a little bit different. To get from this asymptote to this asymptote, it is a full pi, right? But what do you see is happening here? What is the coefficient of pi? 1. What's the coefficient of pi? 3. What's the coefficient of this one? What if I were to go this next one? If I add another pi to that, what's my coefficient going to be of that pi? 5, right? So how do I denote an odd number? Yes, 2n plus 1. So odd is an even plus 1. And then I'm going to multiply that by pi over 2. Because what I'm actually doing is I'm saying every odd pi over 2. That's what this means. So let's do a little side note here. This is every odd pi over 2. So the 2n plus 1 means odd. So every odd pi over 2 that we have. Now I have to denote n is an integer, where n belongs to the integers, right? So where n is an integer. This is just math notation. Epsilon means belongs to. Z just means integer, which we know already. All right? So at every odd integer is where I have those asymptotes. Basically, the moral of the story is draw cosine, bounce off of it, and you're good to go. This is nice. I'm not going to get crazy about this. Definitely not get crazy about this. It's good to know. You have to know that your period is 2 pi, because whenever you go to change up those periods, this is going to be affected. If you look back at these graphs, what is the information that you are asked? What's my amplitude, vertical shift, period, and phase shift, right? You can get all of that information off of your cosine function. You need to know that your period is 2 pi. Beyond that, whatever happens to cosine deals with it. It's just nice. This is just basic information to know. If you know it, great. If you don't, I don't really care. Because your basic working knowledge is this. Not do you know the specifics of how to find the domain and range. Finding a domain and range is good, but I don't want you to get tripped up on this notation. Oh my. I don't want you to get tripped up on this notation as much. Okay. Now let's look at cosecant. We're literally going to do cosecant the same way that we did secant. Except, what's this reciprocal identity? Yes, sine. Cosecant of x is 1 over sine. So basically, anywhere you see sine, you are going to bounce off of the sine function. Bounce off of sine x graph. Graph that first. Anytime you have that, then you just bounce off of that one. Okay? Let's make our graph again. I'm making this a little bit longer just because we know we bounce off of it. So I have to have that extra space. So there's 1, -1, same thing, pi over 2, pi, 3 pi's over 2, 2 pi. go back the other direction. All right, and then if we graph our sine function here, we know we're coming up, passing through, going back down, and then hitting this. Going down, passing through pi, coming back up, and then hitting this. As you well know, this still is a periodic function. So I come up with cosecant. I have asymptotes on cosecant the same way. Here I have my asymptote on the y-axis. I have my asymptote at pi. I have an asymptote at 2 pi. And I just bounce off of that. So here I'm bouncing off. I'm bouncing off. I'm bouncing off. I'm bouncing off. Because sine quote unquote starts at 0, my full period here that I'm looking at looks more of like a complete graph than we do. I'm going to scoot this down. Then whenever I'm looking at a full period of my secant, just because it looks like a half, a full, and a half, where here it's like a full and a full. It's just the difference between the two. Still one period. All right. So then let's come up with all of this information then. The period of cosecant is still 2 pi. Good. Now, what about the range? -1 to 1. Yep, or outside of that, right? So from negative infinity to -1, union from 1 to infinity, because again, this middle part is out, so I'm not worried about that. All right. Now, where are my asymptotes for this one? Yeah, this one's easier because I don't have to worry about odd pi's over 2. This one, every single time I have an asymptote, it's hitting at a pi. So for my domain, I have all of the x values such that x cannot equal n pi. And again, n belongs to my integers. That's that z. So that one's not so bad. All right. Anytime you graph secant and cosecant, you're just bouncing off of your sine and cosine functions. Right? So we spent all that time graphing sine and cosine. Now to graph secant and cosecant, you just bounce off of that. Not too bad, right?